good afternoon for people attending from Europe. Um, Thank you very much for taking time and attending our webinar today. Our topic of today's discussion is going to be vibroacoustic simulation for electrical machines and a multi-physics modeling capabilities. Before starting my presentation today, I would like to address special acknowledgements to my colleagues from Research Development on Electronics Business Unit, Dr. Yashu Lee and Dr. Yumin Shao. The content of today's talk, as I earlier mentioned, will be around the vibroacoustic design overview, the need of vibroacoustic simulation, multi-physics all-flow setup related to the vibroacoustic simulation, from electromagnetic to mechanical, and definitely I would like to share with everyone a case study moving from electromagnetic to mechanical simulation. Starting with vibroacoustic design overview, the main objective to analyze and to predict the simulation, to predict the noise and vibration which are originating from electrical machines. It's very important to understand the entire system related to an automotive application. And as everyone knows, the main focus on efficient simulation for noise and vibrations for electrical machines are coming from the powertrain system environment. The idea of predicting efficiently the noise and vibration originated from electrical machines is to reduce the development cost, is to be able to get faster development cycle, and last but not least, comprehensive and robust solution. Obviously, to achieve these objectives, we should face and we should address accordingly all the challenges. Among all these challenges, we are definitely talking about identification and modeling of contributing noise sources and getting to know the major sources of any noise and vibration within electrical or hybrid electrical vehicle related to the powertrain systems. Those sources are electromagnetic nature, are of mechanical nature, or airflow nature. Today's presentation, we're going to focus on electromagnetic source of noises. The electromagnetic source of noises at the level of powertrain and the electromagnetic source of noises at the level of any electrical machine is developing and is building within the gap domain. The gap is the clearance between the stator and the rotor, or better said, is the clearance between the stationary and rotational part of this low frequency equipment. Obviously, the electromagnetic field distribution within the gap of any electrical machine generate both tangential and radial forces, which are the main source of noise and vibrations in the electrical machine. Important challenges are also related to efficiency and accuracy prediction of these noises. Obviously, the access to the desired outputs are important to be able to properly communicate with any designer. It's starting with an electrical engineer perspective, because an electrical engineer is mainly responsible to properly design an electrical machine from a magnetic topology standpoint, but also with a mechanical engineer, which is more responsible for mechanical integration of such electromagnetic devices. Last but not least, a performance optimization, understanding the level of noise and vibration on any particular electrical machine, understanding the behavior of this electrical machine within the powertrain, and getting to understand the relationship and the interaction between the electrical machine and other mechanical parts other mechanical assemblies, within the powertrain environment. And finally, being able to perform the optimization and tuning design. The ANSYS approach on predicting the noise and vibrations, it's a very, very typical and very well-known approach, moving from an electromagnetic field domain, calculating the electromagnetic field distribution, extracting the forces generated by electromagnetic field, passing those forces into the structural dynamic for sake of getting the resonant frequencies and also the contribution of the electromagnetic forces. And last, going to acoustic field simulation by importing the velocities coming from structural dynamics for sake of acoustic field propagation outside of the electrical machine enclosure or outside of electrical machine housing. In terms of the multiphysics workflow, let's keep it simple in terms of explaining the data transfer between different physics, the data transfer between different solvers, and I'm going to focus on the solution itself with obviously a nature of electromagnetic field distribution. This is a schematic representation of the multiphysics workflow within ANSYS platform, starting from an electromagnetic field simulation and including the low frequency electromagnetic software for 2D or 3D designs, being able to export frequency domain of electromagnetic forces for single RPM or for multiple RPM. Whenever I will refer to single RPM or multiple RPM from this point ahead during my talk, I will definitely talk about the single design point in terms of speed and the multiple design points in terms of rotational speed. We do have capability to analyze 2D finite element solution on electromagnetic side to be able to generate the frequency domain of the electromagnetic forces. We do have possibilities to employ the 3D electromagnetic finite element electromagnetic design for the same reasons. Always on a structural dynamic environment, we use the 3D because the harmonic simulation and also the noise vibration are of 3D nature. This is also very important to understand that the modal and harmonic response is going to augment the information and the knowledge for noise vibration environment. Finally, generating the required data for harmonic acoustic simulation to be able to predict the propagation of audible noise outside of an electrical machine enclosure. In terms of the multiphysics workflow setup, again, coming from an electromagnetic setup perspective, on ANSYS finite element solution for electromagnetics, we are able to account for a template-based solution on housing, pure as a CAD environment, where various options are available in terms of geometry definition and geometry parameter definition for fins, for ducts, for caps, for foot and flanges, being able to parameterize all the dimensions related to these components, and being able to provide with a 3D housing or 3D enclosure of any topology chosen in our design design space. Electromagnetic field analysis is going to occur on a design space related to electric machine simulation, and typical design space for electric machine simulation relates to a stator with its winding configuration as an excitation for the electrical machine. It's continuing with the rotor design, could be a permanent magnet rotor, could be a wound rotor design, could be a brushless, could be an AC machine as well, an induction machine, switch reluctance motor configuration. And a typical simulation related to electromagnetic field analysis relates to the magnetic transient simulation on a 2D or a 3D configuration. It's very important to understand why magnetic transient plays a significant role on accuracy of noise and vibration prediction. It's just because magnetic transient in ANSYS is coming with the most comprehensive capabilities for magnetic design, considering nonlinearities, considering dynamic field distribution in terms of dynamic diffusion of magnetic field in conductive domains, and also a motion-induced electromagnetic quantities which are responsible for efficiency, are responsible for losses, and also electromagnetic force distribution, which we've been able to see. Electromagnetic forces are responsible for noise and vibrations. Obviously, we are able to consider 2D when the entire configuration, entire design is fully symmetric and balanced from both geometry and from electromagnetic field distribution standpoint. But 3D, it's required where end effects are no more negligible or some other asymmetries are happening, like static and dynamic eccentricities, or even tilting rotor configuration as well. In terms of harmonic force calculation, again, the force calculations happens within our finite element electromagnetic footprint. And basically, we have employed two different methods to generate fast harmonic force calculation and also to generate more reliable and more accurate force calculation. The first method relates to element-based solution, and based on graphical user interface selection, the user can select the objects within the 2D or 3D domain space, which are included into the final force calculation for noise vibration prediction. In the same time, we do have a second method. It's called object-based method. And this object-based method, it's a fast computation and fast prediction of the noise vibration, and we're going to see the difference between the two methods as well. In terms of the object-based simulation, assuming a 2D or a 3D topology, we can insert in an integration sheet in a 3D environment to be able to calculate the total force distribution across the air gap facing the object we want to calculate the total force, or we can use lines in 2D environment to be able to integrate over this line the force calculation for the same reason. We can see in the zoom area of a stator teeth, those lines which are helping integrating the force calculated electromagnetic forces and transferring those forces into a frequency domain for harmonic response simulation. Obviously, we can place those dummy objects in terms of 3D or 2D between the band and the stator for stator force computation. If this line or surface is going to be located between the band above the band, which the band is the vacuum object or air object separating the two stationary and the rotational parts of the electrical machine, we definitely can calculate the stator force computation. And in the same time, if that sheet or line is located below the band and facing the rotor, we're going to be able to transfer the rotor force frequency domain data into the harmonic response as well. In terms of the 3D, we can separate, the teeth tips from the stator. The 3D and 2D is the same comment. It's either skew or unskewed configuration, and we're going to be able to focus and to be able to narrow the design space, the design objects where we're going to be able to calculate the remote force or the total force distribution. This can be applied for all skewed teeth, irregular shapes, or eccentric cases as well. Again, this object-based is very suitable for a fast noise vibration prediction. This is very important to understand how properly set up an electromagnetic simulation design to get a proper force excitation into the mechanical environment. This is very important, to understand the parameters set up on magnetic transient environment and how these parameters affect the resolution and the data is going to be transferred into mechanical environment. In the finite element solution electromagnetic design, we are able to set up the time step for transient analysis, and the time step value we're going to set the highest frequency we're going to be able to analyze in a mechanical environment. The single side spectrum of the maximum frequency available in a mechanical simulation, it's equal with a half of the frequency given by the time step. Equally important is to be able to understand the relationship between the constant speed defined in the motion setup within magnetic transient environment, the fraction which requires the symmetry used in electromagnetic finite elements simulation, and the frequency step. The frequency step is the frequency resolution is going to be analyzed during the harmonic response simulation. The frequency step relationship is given by the speed of the electrical machine in radians per second multiplied by the fraction which represents the multiplier, the symmetry multiplier. In other words, to be able to reduce the frequency step in a mechanical response at a given speed, you should be able to increase the symmetry multiplier, and the minimum frequency step you're going to be able to get is for the full cross-section of a radial field distribution electrical machine configuration. These two components or these two parameters are equally important when you move into harmonic response simulation to be able to get the highest frequency resolution as well at the smallest frequency step resolution as well. The stop time in electromagnetic transient should be long enough for one fraction period of a steady state operation, because to get more accurate noise vibration, the data transfer from electromagnetic to harmonic response should happen at the level of steady state condition on electromagnetic side. And as previously said, the fraction which is the symmetry multiplier control the lower resolution mechanical resolution simulation as well. In terms of modal and harmonic response, modal analysis will gonna help providing the information on the frequency resonant frequencies, which are the structural resonant frequencies, and has nothing to do with any electromagnetic excitation, with any electromagnetic field distribution. You might use or you might not. This is not, strictly required, but modal analysis we're going to support and we're going to help further harmonic response and further harmonic acoustic simulation. From that reason, I include the modal analysis brief explanation on a proper setup and simulation. On a modal analysis, to be able to calculate the modes and the mode shapes is going to going to choose the maximum we want to find. In this example, 20, 10, 20, 30, or even larger, most depends on the topology chosen. During the model analysis, we definitely calculate the effective mass ratio, and it's going to be reported after the simulation. Harmonic response follows the model analysis simulation, where the boundary condition is going to require a fixed support, and this is very important to understand why we are generating from very beginning, from a magnetic design, the housing or enclosure for electrical machine, to be able to better analyze the fixed support definition in a given assembly environment. And here again, we are talking about the powertrain assembly, where the electrical machine is inside of an enclosure, inside of a housing, and the housing is going to be mounted on a special platform and is going to interact with other mechanical components through an external shaft, through a gearbox, and so on and so forth. In terms of setup analysis, harmonic response is coming with two options. It's coming with a full mode solver and a mode superposition method. There are two different solver options to be able to speed up the harmonic response using a mode superposition method, or to get more detailed and more comprehensive full options where the full matrix of the system is going to be solved. Damping is also very important, and the damping value will gonna be set up properly into the harmonic response simulation. In terms of electromagnetic input, because here in harmonic response, the electromagnetic input is critical, we can import a single RPM from finite element electromagnetic simulation on a desired object from a design space, in our case, the stator teeth or the rotor configuration. And on the right-hand side, you see what we mean by imported load from the two options we discussed. From an element-based, the surface force density is going to be calculated in finite element electromagnetic solution, and from a nodal force calculation, we calculate based on the mesh topology on a mechanical design space the force density, and the force density will gonna be the input for the harmonic response solution. Or you can get into object-based as a remote load, and as I mentioned earlier, on a given line for a 2D or a given 2D sheet for a 3D topology, we are calculating the total force, and the total force becomes the remote load input for harmonic response. Besides that, the moments are going to be calculated after electromagnetic simulation is completed and transferred into frequency domain for harmonic response simulation. In terms of importing multiple RPM, the comments I already made was related to single RPM for a single given speed. We are able to perform a discrete Fourier transformation on electromagnetic transient forces, the way I mentioned, element-based or object-based, and transfer these frequency domain forces into harmonic response. On a multiple RPM, we are able to calculate multiple speeds as a multiple design points within magnetic transient simulation, and we are able to do discrete Fourier transformation in the way we do for object-based for every single speed considered in magnetic transient simulation. Here we can see, for example, in an object-based environment, importing the load per RPM, and under imported remote load, the user will gonna be able to see the values of the forces for each individual speed considered in magnetic transient simulation. The beauty of getting the full load from electromagnetic simulation is that in harmonic response environment, the user can suppress or unsuppress a certain data, a certain speeds for a final noise vibration prediction, and always coming back and unsuppress or suppress, certain speeds to be able without simulating the magnetic transient design again. The final point is going to move into harmonic acoustic. Before understanding the harmonic acoustic simulation for electrical machine, we need to understand as the users, we need to understand how to properly model the domain. And it's very well known that for domain modeling, we are considering, infinite free space around it. We consider homogeneous isotropic inviscid, which relates to how the wave are traveling through the domain boundary without the reflection. And this is very important because the wave absorption condition needs to be considered to properly design the propagation of acoustic field outside of the enclosure or outside of the electrical machine housing. And here we're going to definitely talk about the PML, which stands for perfectly matched layers, which reflects the least amount across the widest range. And this is more appropriate boundary condition, as you can imagine, for an harmonic acoustic simulation on electrical machine design. In terms of the perfectly matched layers, this is the theory behind of it. And very important is to understand what type of the PML layer should be considered. The difference between the regular versus irregular configuration, which here, it shows the cubic versus convex. A short description of the perfectly matched layer, you see the vibration source in the right hand side, which the vibration source is nothing but the electrical machine inside of the housing. You see the radiation space, which represents the acoustic region, which is the immediate region around the electrical machine and its housing. You also see the symmetric, physical region, which is the PML, which again is the perfectly matched layer, which is built outside of the acoustic region. And also we do have the symmetry plane and the sound soft boundary, where we need to enforce the Dirichlet boundary conditions as a sound pressure be equal to 0, far enough from the vibration source which are generating or propagating the audible noise outside of the housing. In terms of the proper acoustic setup, again, we are facing, two major regions. We are facing the acoustic region and we are facing the physical region. For acoustic region, which is the outside of the source of acoustic noise, it's recommended the radius to be half of the wavelength, where the maximum wavelength is given by the minimum frequency. And remember what I mentioned earlier, the minimum frequency is given by the fraction, the symmetry multiplier, into the electromagnetic design solution. As far as physical region goes, the recommendation is to get, a quarter of the maximum wavelength based on the same formula. And in terms of the element size, to get an accurate acoustic representation, you see here, it's 1/6 if used quadratic elements, or 1/12 if linear elements are used. And this is from a minimum wavelength, which is given by the maximum frequency. Again, maximum frequency given by the time step analysis, the time step value set up in magnetic transient solution. For the physical region, at least 4 layers of elements are required to get more accurate representation. In terms of harmonic acoustic, this is a schematic representation on animated slide on how to define, how to introduce an acoustic domain, how to introduce in physical domain, obviously how to set up the acoustic domain definition in terms of match layer irregular PML configuration. Here you know how to properly set up the directly boundary conditions outside of the physical domain to enforce the sound pressure to be 0. And in the right-hand side, definitely the imported loads for harmonic acoustic relates to the velocities coming from harmonic response. In harmonic response, besides displacements versus frequency, are calculated velocities, are calculated accelerations, and the normal components of the velocity on the surface nodes are going to be exported into harmonic acoustic. And here we see in the right-hand side the distribution, the field distribution of these velocities. For the last part of